Okay, welcome back. So I wanted to come back and I wanted to do one more example. I thought it'd be, we did only one example, so let's do one more example for using the two sample z-test. So I thought it'd be good to do at least one more example. So here's another example that we could do. Okay, so let's look at this. So it says the means of the number of revolutions per minute of two competing engines are to be compared. 30 engines are randomly assigned to be tested. Both populations have normal distributions. The table below shows the result. Using a 5% level of significance, do the data indicate that engine 2 has a higher RPM than engine 1 on average? Okay, so that's what we're going to test. So now, the claim is what? The claim is that, let's see here. Let me just make sure I don't want to go off the, so the claim is that what? Engine 2 has a higher RPM, so revolutions per minute, on average. So again, keywords, on average, than engine 1. Okay, so that's going to be the key here. Okay, just want to make sure. So here's the claim. So now how do we set this? Well, let's make this mu2. Okay, again, it doesn't matter which one you make mu1 or which one you make mu2, as long as you stay consistent with what you have. You'll get the same result. Again, test this, try it out, and prove it to yourself. Okay, so if you want to make this mu1 and this mu2, the population of times here, mu1, and the population of times of engine 2, mu2, or if you want to make this mu2 and this mu1, doesn't matter. As long as whatever you choose, you stick with it and you're consistent throughout the whole test. Okay, so let's make this mu1. Or no. Yeah, let's make this mu2. Let's say this is the population of times, revolutions per minute. The average population for the average let me think. So let's make this the populations of the RPMs, the rate. The population of engine 2, the RPMs from the population of engine 2, mu2. And let's make this the population mu1. Okay? And now, if mu2 has a higher RPM on average, well, then this would be greater than, right? So we're saying that mu2 is greater than mu1, right? Okay. Now, how are we going to write this for our hypotheses, though? Well, our hypothesis is always mu1 followed by mu2. So if mu2 is greater than mu1, that's the same as saying mu1 is less than mu2. So with that in mind, our null and alternative hypotheses will be mu1 is less than, mu1 is greater than or equal to mu2 versus mu1 is less than mu2. So right here, okay, just so you see this, right here, this is the same as that, right? So make sure you see that, right? So the way we define it, we just wrote out the symbols, right? So we said this is the population 1, or no, 2. This is population 2, this is population 1. And so when we write it out in symbols, we get mu2 is greater than mu1, but that translates into this, right? We're just flipping them right in it in the opposite direction because we always have mu1 followed by mu2 in our hypotheses. Okay? So now this is the claim. Okay? So now that's where we're starting at. And in this case, it's a left tail test. So that's step 1. Step 2, we're going to assume the null is true. And in other words, mu1 minus mu2 is 0. No difference. Okay? And then 3 is our data. And here's the data that they give us. So again, alpha is equal to 0.05. And here's the table. So the table values is this. Okay, so here's engine 1, engine 2. This is X bar and sigma. Okay, population standard deviation. So they give it to us. And so now X bar 1 equals 1500 RPMs. X bar 2 equals 1600 RPMs. Sigma 1 equals 50, and sigma 2 equals 60. Okay, so that's the information they give us. Okay, so now, again, the main thing we want to know here is the sampling distribution of X bar 1 minus X bar 2 normally distributed? Well, let's quickly just look at that. Well, they told us that the population of RPMs, right, for both engines are normally distributed. And we have random samples. So that means that we do have the sampling distribution. So we know, based on this information, right, that X1 is normally distributed and X2 is normally distributed, right? That it's going to have a standard deviation mu1 and sigma 1 over the square root of n, and mu2, or mu1, or n1. And then the second one's going to have a mean of mu2 and a standard deviation of sigma 2 over the square root of n. Okay, so we know that. Okay, and since we know that, we automatically get what we need, which is going to be the sampling distribution of X bar 1 minus X bar 2 is going to be approximately normally distributed, and it's going to have a mean of mu1 minus mu2 and a standard deviation of the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so I'm just going to write that out because that's, again, the important step of 3 is we're writing down the information in the data to verify that we have the distribution we need, which is this. Okay, so now that we know that, now we can go to step 4, right? And step 4 is our test, and here's where I'm just going to use the calculator. So again, I know sigma, and it's the difference of means, so I'm going to use the 2 sample z-test. And so now all I'm going to do is put in the information I need. Okay, so let's do that. I'm going to grab the calculator. So I'm going to go to stat tests, go down to number 3, two-sample z-test. And I'm using stats. So what are the stats? Okay, what's sigma 1? Sigma 1 is 50. Sigma 2 is 60. X bar 1 is 1500. N1 is what? 30. They took 30. Let me go back to the problem. 30 engines are randomly assigned to be tested. So 30 each. Okay, so N1 and N2 are the same again. That won't always be the case. So N1 is 30. X bar 2 is 1600 with N2 equal to 30. And in this case, our alternative hypothesis is left tail, which is less than. So I'm going to choose less than. And now I'll just hit calculate and look at that. Our p-value and our z-score is really, really, really significant. Okay, so here's what we get for our test statistic. Z star turns out to be negative 7.01. That's huge because remember, how big does the z table go on either the negative table or the positive table? Well, 3.99 is the highest I've ever seen a table go. This is negative 7.01, so huge. Which, if you look at the p-value now, you'll agree. You'll know why. Because the p-value is 1.17 times 10 to the negative 12th power, so essentially it's 0. So again, if we do the p-value method, we're definitely going to reject the null because the p-value is almost 0, practically 0. So it's going to be approximately 0, and of course that's always going to be less than alpha equal to 0.05. And so 6 is, therefore, we reject the null hypothesis. And so 7 is, again, way we state the conclusion is, at an alpha level of 0.05, and since the claim is the alternative now, so at an alpha level of 0.05, there is very strong evidence based on the sample data that the RPMs for engine 2 are higher on average than the RPMs for engine 1. That's it. Okay. Well, that's the other one I want to do. So again, do the examples in the textbook. Do these examples. Try to do these examples without looking at the solution. That's always been my advice. You get much more better feedback as far as your understanding if you try to do these before I show you the answers. But next time we'll continue on, and next time we're going to talk about how do we do these hypotheses tests when we don't know the standard deviations for the populations. Okay? That's where the t distribution comes back. See you then.